Hello Internet. Today I will talk about binary exploitation. First of all, I want to introduce you to some resources that I often use. First, try HackMe. It's a pretty good website for hacking challenges. It also includes Poon 101 challenge, which is my favorite challenge in binary exploitation. To give you some foundations. Also, I will recommend very highly the Shell Coder Handbook. This book gave me a strong foundation about binary exploitations in different environments, same as hacking the art of exploitation. Last but not least, my favorite website. It converts the high-level code to your assembly language code. It depends on which compiler you use. You can select whatever you want. So I will start with some simple challenge on Try Hack Me. It's called Pwn 101, as I said before. I will solve the second challenge, which is Pwn 102. In this challenge, I will focus more about how to read an assembly code, how the operating system manages the memory layout in the ELF executable on Linux environment. So this is our file. I will check first the security applied on this file with command called checksec. I will provide the file with -- file and provide the binary name as an argument. If you analyze the output, we'll get that rel row is full. I will explain that in another video maybe. There is no stack canary. Okay, that's pretty good. Basically, stack canary is a variable who sit between the two stacks layout, and it prevents the overwrite of this variable from stack to another stack to protect the normal flow of the program. Our third flag is non-executable, so we can't run an assembly code that's it in the stack. Like we can't execute, it doesn't have executable flag in that memory section, which is the memory stack. Position independent executable, it's enabled. I will probably also explain this protection in another video and how to bypass it. Okay, let's start. It's a good science. Like also we have symbols, which means it's not stripped file. We can read the function's name. This will help us a lot in the analysis. Okay, we'll need for sure a tool called GDB, Geno Debugger, which is very handful and useful tool. It's a pretty old tool, but it's very stable and strong. First, I want to check. I want to do this command echo set this assembly dash flavor to Intel, because I'm used to read the Intel syntax in the assembly code, and I will recommend this for you also. And I will pipe it to .gdb init file. Let me open this program with GDB now. Okay, let me clear this screen. And I will start with this as main. This will disassemble main for us. Okay. If we check carefully, we have the Intel syntax. So I will explain those two instructions. What does they do when the first function, the previous function, who's calling main, it will have its own RBP and RSP. I will illustrate this here. Okay. Assume that this is the stack of the caller function and this is the stack of the main function. So the RBP was here, the base pointer, as you can know from its name, it's register based pointer, and the RSP means register stack pointer. So this means it will point to the top of the stack and the RBP will point to the bottom of the stack. So when main is initiated, we will push the RBP. So what basically will happen here in the stack, this RBP value will be pushed to here and the RSP will decrease because the stack, the higher address, stack go from the higher address to the lower address. It will go like this. Okay, basically we pushed the RBP in the stack, the new stack. Then we move the RBP to the RSP. Okay, So the new RBP will point to the same level as RSP pointing to. So here we have a new stack. The RSP will move like this, and the base pointer will be fixed. So that's how it works. Let's continue discovering our program. After we pushed the RBP and moved the RBP to the same level the RSP was, in the instruction 4, the RSP is subtracted by 70 bytes in hex. So if we want to know what is 70 bytes in hex, we can basically do this. It's 112 bytes. So let's draw this very quickly. Okay, the stack will move upward with 112 bytes, which is 0x70. Okay. Also, we are setting the EAX to 0. This is probably because we want to pass an argument to a function. You can see the conventions of calling a function, and it's predictable. The setup will be called or any function because we set the variables to pass it to this function. We are setting EAX again to 0, and we call banner. This is probably an output function that print outputs. We'll check that later. And those two lines are pretty interesting. Putting this value, bad food, to RBP -4. Add those values here in the stack. This is RBP -4. So I will pass this here. And also here, it's putting this value in RBP -8, which is 8 byte. I will do the same here. Like this. Okay. Then we are moved EAX to ESI. This is also probably for calling a function. And RDI, EAX was 0. RDI, we are passing RIP plus this numerical value, which is this value. I will examine this value quickly with the operation examine, and I will precise the data type of this. I will check the string data type. Okay. We got this string. We are passing this string. This probably will be passed to printf function. Yes, I guessed right, because printf accepts the format string. And we are loading the effective address of RBP -70, which is this address we reserved before, to RAX. Okay, then RAX is pointing to this address. Okay, to the RBP, the RSP. What also is happening, we are moving RAX, which is also the buffer address. I will call this a buffer. It will pass it to RSI, and it will pass this variable. I will examine this quickly. The %s to the RDI, and we are calling the scanf. So what this basically means, we passed 2 argument to a scanf. It will be equivalent to scanf %s and the address of the buffer, like this. So the program will scan, then it will compare this value with the RBP -4, which is this value, the bad food value. And if it's not equal, it will jump to main plus 148 instruction, and this 148 instruction, it will jump here. So what will happen here is the program will exit normally and print a function with put. It will print, and it will print a message with put. Let me check this message quickly. I will examine it with this. I'm feeling dead because you said I need bad food. Okay, this is probably our lost flag. It's not our win flag. So after the comparing, we do another compare, which compare the 0x, this value here, to RBP -8. connect to this value here, okay. Then also, if it's not equal, it will go to this and exit normally with the lose and the fail flag. And of course, this is not what we wanted. We want to bypass those comparison and reach to the system function, which is basically, I will see what this program is passing to system, so I will examine, and of course it will be the bin/sh, which is the full control of the system. So my plan is to make those variables in the stack equivalent to those variables, because we want to pass the compare check. We have the scanf privilege. It means we have the writing privilege in the buffer point. So if we can write toward with no limit checking, we can overwrite these values. So basically, we need padding here, a dummy data, and we need to overwrite with our actual values here. So how many padding we need? If we said this consumes 0x8 bytes, so we need 0x70 minus 0x8 bytes as a padding, and we need the payload. We need to add this address first to the payload and this address also to the payload. This is our payload. Let's implement it with Python. So we need this amount of padding and the rights values. First, I will run the program normally to see what it does, because all what we did was passive scan or static check of the binary executable. We didn't interact yet, and now we'll interact. Let's see. I need the bad food to feel dead. Am I right? I'll type everything here. I'm feeling dead because you said. Okay, whatever I will write here, even if I try to overflow the program, nothing will happen because we need to overwrite with the right values. So I will craft our payload. I will do this with our magic tool or programming language, which is Python. I will open a file called exploit with them, and I will import tune, or no, not yet. I will import struct. You know what? I'll import tune for now because it's important to use this tool for later usage. Then I will initiate padding with A's, with any garbage values, and I will add a byte specifier. Then I will multiply this value with 0x70 minus 0x8. This padding also, I will do the value one equal. Okay, I forgot the value one. What it was 0 C0. Okay, to convert this value here to a little Indian notation, \x 33 \x ff \x, oh my god, /x C0 0. I think that's good. I will rename this to value 1 and \x p3 \x c0, and I will add the extra offset because it's the address had to be 4 bytes. The memory address had to be 4 bytes. X 0 0 \0 0. Okay. Then I will concat payload value 1 padding plus value 1 plus value 2. Then I will print payload, and I will check, I will test it very fast. Okay, I forgot to source to my local environment. Wait, okay. I have a typo, let me fix it very quickly. Okay, very good. Add value 2 plus value 1. Then what I'm going to do is to open the process with function called the process, and I'll provide the file name. I forgot the file, it was very big. Okay. Then I will do p dot receive p sound line the payload or payload. I will delete this. Then p dot enter active. Back. Nice. We got the winnable flag. I got yes, I need copy to code.